Sounds good. And before we even continue on with the notes, I do want to talk a little bit about something that Michael came up with or asked about last class that I honestly haven't really thought about too hard since I didn't really do my research or anything in calc or limits or anything like that. I haven't actually thought about this in a long time. And Michael asked before we talked about graphs that look like, for example, this graph here. It's a piecewise function. Oh, wow, we got a train of kids coming in. We have a piecewise function and it goes all the way up on one side and on the other side, it's like flat. And we said it did have a horizontal asymptote. And that was really confusing because I feel like our whole lives we've been told that asymptotes are things where the graph gets really, really, really close to and it doesn't touch it, right? I feel like that's the definition that we have in our minds of an asymptote, right? Unfortunately, in calc, the definition of asymptote is a little bit different. The definition of, oh my gosh, the definition of a horizontal asymptote is the limit as we approach infinity and the limit as we approach negative infinity. That's all a horizontal asymptote is. So I did some digging online and yes, a function can touch its horizontal asymptote. Even if it's a straight line, the constant function, it still has a horizontal asymptote because it has asymptotic behavior, long-term behavior. So I know it sounds a little bit weird that a function can touch its horizontal asymptote, but that's the calculus definition of an asymptote. Okay, so I know it sounds a little weird, but that's how we're going to define it for this class. Okay, so we talked about the difference between a vertical asymptote and a horizontal asymptote, how we define them using calculus. A vertical asymptote is when we take a limit as x approaches some number and we get plus or minus infinity, either from the left or from the right or both. And a horizontal asymptote comes across when we either take the limit as x approaches infinity or negative infinity and we get a number. Okay, so that's where the horizontal asymptotes come about. And we did some tricky questions that I thought were fun, but you probably didn't. And then we went through examples of graphing a function and then taking a limit from the left or from negative infinity and positive infinity and try to find if we had an asymptote or not. Okay. I think we left off with example 5 where we had a piecewise function, we graphed it, we realized, okay, the right long-term behavior didn't really tell us anything, but as we went, as x approaches negative infinity, the graph approaches 0, so y equals 0 was our horizontal asymptote. Okay, let's go to example number 6. Okay. There was example number 6. We're looking at the limit as x approaches positive infinity. By the way, is there anyone who needs the notes? Okay. We're approaching positive infinity, and we have a polynomial over a polynomial, right? Anyone remember what these are called? The polynomial. Rational functions, good. Rational. Okay, and unlike the other questions that we've talked about, I don't know the graph of this, right? I can't, from the top of my head, I can't graph this function. So maybe I can't do the same thing that I've done before with my other limits, okay? So maybe there's a way I can do this algebraically, okay? First of all, looking at this, is there anyone who might have seen this in high school and might guess what this limit is? Sam?
Limit's 1 over 2.
1 over 2, and why did you get 1 over 2?
Because when you have a rational function, you got to look at the largest matching exponent, and then you use those coefficients.
Yeah, right. We have x squared and x squared. Those two functions kind of, they increase at the same rate pretty much, right? Since they both have a squared. And because they have the same power on the top and the bottom, the convention is to take the coefficient of the highest term on top, the coefficient of the highest term on the bottom, and put them on top of each other, okay? Now, in the future, we will be using this technique, but let me just kind of show you why this technique works. And then we'll talk about why this method might not be helpful to us in other cases, okay? So I'm going to take this limit And I'm just gonna repeat it with the x squared minus 6x plus 3 over 2x squared minus 7x plus 6. Okay, and I'm gonna take this whole thing and multiply it by another glorified 1. Okay, so I want to multiply it by 1. Okay, but instead of writing 1, I'm gonna write 1 over x squared over 1 over x squared. We all agree that's 1? Yeah, I know it's a funky one, but it is, right? The reason I chose x squared is because it was the highest power, and maybe I want to divide everything by that highest power. Okay. All right. Well, why don't I just multiply it through, divide every term by x squared, essentially, right? So this would be the limit as x approaches infinity of x squared over x squared minus 6x over x squared plus 3 over x squared. Same thing in the denominator, right? 2x squared over x squared, 7x over x squared, 6 over x squared. Okay. That might be helpful because now I can cancel out the x squared and the x's in the middle terms, right? So this would turn into the limit as x approaches infinity. X squared over x squared is 1. We got 6 over x, and the last term doesn't change. Then we have 2 minus 7 over x plus 6 over x squared. Okay. Now we're getting closer to something that might help us, okay? Now, as we have been looking at graphs of rational functions, we know what the graph of like 1 over x is, right? That looks like this, right? And what was the limit as x approaches infinity of 1 over x, for example?
0.
0, right? And what about 1 over x squared? That graph looks like this. What's the limit as x approaches infinity of 1 over x squared?
Still 0.
Still 0, right? Actually, if I take 1 over any sort of x, the limit as x approaches infinity is going to be 0. And even without graphing it, you can look at it and be like, okay, 1 over a really, really big number, infinity, is going to be about 0, right? Okay, so this 6 over x here, as we take the limit as x approaches infinity, that's going to be 0, right? Same with the 3 over x squared, and the 7 over x, and the 6 over x squared, right? All of these guys are going to 0. That's going to 0, 0, 0, and 0. Long-term behavior, right? Okay, but the 1 and the 2 are constant functions. And as we look at the limit as x approaches infinity of a constant flat line, that's going to approach those numbers, right? So that's why we're left with 1 over 2. Okay, so now I don't expect you to use this method when you see questions like this, and we'll talk about why in our next example. Okay, so this is a good method, but it's kind of time consuming and it doesn't work all the time. Let's go to another example. Okay. Example number 7, we have the limit as x approaches infinity of x squared minus x plus 2 over x. Okay, looks like the highest power of x is 2. So why don't I just try the method? Okay, let's try the method. So I'm going to take the limit as x approaches infinity. Why don't we just divide everything by x squared, see what happens? X squared over x squared minus x over x squared, or x over x squared, yep, minus 2 over x squared over x squared. So just dividing by x squared, right? Okay. Well, x squared over x squared is 1. That's nice. We got 1 over x and 2 over x squared. And on the bottom, we've got 1 over x. Okay. Now, we've got these guys going to 0. But on the bottom, that's going to go to 0 too, right? Anything over x is going to go to 0. So this is 1 over 0. That's not going to work, right? So using this method is not the best method, It really only works when the degree of the numerator and the degree of the denominator match. And even then it's kind of time consuming, okay? What do you think this limit is?
C does not exist.
Why don't we take a even closer look? If you scroll down, you'll see the graph. Okay, does this change your mind? What's the limit as x approaches infinity?
There's two, I think.
Really? If I extend this line and go further up and further up, where do you think that's going to? It's going to positive infinity, right? No, you're good. All right, so as we're getting closer and closer and closer to positive infinity, getting those long-term answers or long-term positive values of x, this limit is actually going to infinity, okay? Now, without even graphing it, let's try to figure out why it's going to positive infinity, okay? Let's see. Okay, on the bottom, we've got the highest power of x is 1, right? And if I took values of x, let me do, let's go down here. Oh my gosh, okay, we'll just go down here. Okay, on the top, we've got something where the highest power is x squared. So why don't I just take a look at the function x squared? And on the bottom, we got x, okay? Now I know there's a bunch of stuff on the top, but let's just focus on a degree 2 polynomial, okay? Let's plug in some x and y values for each of these functions. Okay, now they start off at the same point, right? When x is 1, y is 1 for x squared. When x is 2, x squared is 4. When x is 3, y is 9. When x is 4, y is 16, right? Now if we go over to x, when x is 1, y is 1, that's fine. When we go over to x equals 2, well, y is 2. X is 3, y is 3. X is 4, y is 4, okay? Can we see that x squared is increasing much, much faster than x? Yeah, right? So if I take something where I have an x squared on top with a bunch of other stuff, and there's an x on the bottom, the numerator is increasing much, much faster than the x on the bottom, right? So the numerator is increasing really fast. Okay, and in the denominator, it's increasing, but it's not as fast, right? So slow increase, okay? So if we take a look at long-term, really big x values and plugging it into the function, we're gonna get something extremely big on top and something big on bottom, but it's not gonna be as extreme as what we have on the top, okay? So because of this, we're gonna get really, really, really large values as we go to higher values of x. And that's why we're going towards infinity. When we divide a really big number by a smaller number, we're still at a really big number, okay? So this is why whenever the degree of the top is bigger than the degree on the bottom, we're getting something that's infinity. Okay. Does that make sense? Cool. Okay. Oh, yeah.
If you add 1 to the denominator,
Mhm.
x, is that just the first class and to the left, right?
The vertical asymptote, yeah, to the left.
Still like some sort of like linear asymptote. Like you could almost do like the asymptote is x minus 1.
X minus 1?
If you graph the function of x minus 1, you would never.
So are you saying if the denominator was x minus 1?
No, I'm just
Oh.
saying it never. If you graph x minus 1.
Oh,
it looks
yeah.
like the asymptote.
Yeah, there still is a okay, it's not a vertical asymptote, but there definitely is an asymptote of this function. I'm sorry, Sam, I kind of zoned out here. We don't have a we don't have a vertical asymptote here, but we do have actually no, we do have a vertical asymptote here. Okay. It does look like we have a linear asymptote going here, but it's not gonna like approach a number and stay at that number, right? As we go far and far and far to the right, it's gonna keep increasing, but yes, there is some sort of linear asymptote going on there. But that doesn't affect the horizontal asymptote. Yeah. good observation there. Any other questions on this one? Yeah, that one is, the linear asymptote doesn't affect the horizontal asymptote. Okay, perfect. Let's move to the next page here, okay? Here I'm gonna tell you the strategy. So the method that I used in the example, 2 examples ago, I don't expect you to do, because we have a really easy way of solving these limits, okay? We're gonna focus on solving the limit as x approaches positive infinity. Because we don't have enough time, if you're ever curious about the limit as we approach negative infinity, just ask me in office hours, okay? We're just gonna focus on positive long-term behavior. Negative isn't that bad, but we'll just not touch it, okay? So we have a limit of a rational function, which means a polynomial over a polynomial, okay? Now, the way we represent rational functions is we have f of x in the numerator, g of x in the denominator. Okay, so we have something up top divided by something on the bottom. F is on top, g is on the bottom, okay? Let's say the degree or the highest power of f of x is the same as the degree of the the highest power of g of x, okay? What we do is we're gonna take the coefficient of the highest power in the numerator, divide it by the coefficient of the highest power in the denominator. That's our limit. Okay, so just taking those highest coefficients. Okay, if we have the numerator exceeding the denominator, so we have a higher power in the numerator than in the denominator, the limit's either going to be infinity or negative infinity, depending on the signs of those highest powers. And we'll talk about what that means in the next couple examples. Okay, now if the degree of the numerator is lower than the degree in the denominator, this limit's going to be 0, kind of like 1 over x squared, something like that. That limit's going to be 0. Okay, let's do a few examples here. And I promise I'll let you on your own, but we'll do all of these together. Okay. Limit as x approaches infinity, 2x to the 5th over 5x squared minus 4. What's the degree of the numerator? 5. Degree of the denominator? Good. The numerator exceeds the denominator. So it looks like we have something like number 2, where the answer is either going to be positive infinity or negative infinity. Which one is it? Positive, right? Because the coefficient of the highest power in the numerator is 2. The coefficient of the highest power in the denominator is 5. They're both positive. So that's why we're getting positive infinity and not negative infinity. Okay. All right, next example, we got x to the 4th degree is 4. X squared degree is 2. Looks like we're exceeding in the numerator. So looks like we got another infinity or negative infinity example here. Which one is it? Positive, negative, good. And that's because, well, we got 1 as our coefficient of the highest power on the top, -3 as our coefficient of the highest power on the bottom. We've got a positive, we got a negative. Looks like when we multiply, we're going to get negative infinity. Any questions so far? All right, one more example. We got negative x to 6 over negative 2x plus 3. Highest power in the numerator is 6. Highest power in the denominator is 1. Is this going to be infinity or negative infinity? Infinity, good, because even though both of them are negative, when we multiply 2 negative numbers together, we get something positive. Okay, any questions so far? Good. Okay, next example, we got x to the 4th, highest power 4. We got x to the 12th, highest power 12. What's this limit going to equal?
0.
0, good. Degree in the denominator exceeds the degree in the numerator. Going on further, we have this one. Okay, degree in the numerator is 10. Degree in the denominator is also 10. What's my limit?
3/2.
3/2, perfect. Okay. Whenever the degrees match, we take the highest coefficient on the top and the bottom. All right, last one. Looks a little bit crazy. What do you think the degree in the numerator is? Okay, so you're saying 1, right?
1.
Why is it 1?
Square root of x squared.
Yeah, essentially you're kind of distributing this guy. So essentially it looks like it's 2, but we also have a square root going on. Essentially, we have something that looks like the square root of x squared. Okay, the long-term behavior, we're looking at a square root and an x squared as our highest sort of power. A square root cancels an x squared, so we're left with x. Okay, so I know it looks a little weird, but the degree of the numerator is actually 1. Okay. Degree of the denominator is 1. Okay. What do you think this limit's going to be? Good. Square root of 2 over 4. Okay. Because I know it looks weird, but technically the coefficient on the highest power of the numerator is about the square root of 2, right? And the coefficient on the denominator is 4. So we're going to stick numerator and denominator, and we're good. Any questions on these guys? Oh, Troy? Okay, I promised I'd let you on your own for this. So you're actually not going to start a new set of notes for now. All right, I don't know why I titled it that. I didn't realize it would show up. All right, first one, I want you to find this limit here. All right, sounds good. So why does it say, oh, okay, I was like, where's 20 on here? No, that's how many people signed up. Okay, good. I wish I wrote down these limits now. Darn it, the degree in the numerator was 2, right?
It was 3.
3, okay.
It was actually 2.
It was actually, and then the degree in the denominator was 2, they matched. So we take the coefficients of the top and on the bottom. So that's why we got 3 here. Any questions on the limit, even though it's not there anymore? All right, let's move on to see who's at the, oh, Jude's at the top. All right, let's keep going. I'll make sure to write these down. All right. Sounds good. We got infinity. Most people got infinity. Why was it infinity?
Because it was positive, it was higher.
Yeah, 4 was the highest power in the numerator, 3 was the highest power in the denominator. It's going to infinity or negative infinity, but since 3 and 6 are positive, it's going to be positive infinity. Any questions? Sound good. Let's go on to the next one. Oh, looks like Sam's taking the top. All right, next one. Ooh, okay, so we got a lot of people saying 0. The correct answer was negative infinity. And why was it negative infinity? What was the highest power in the numerator?
3.
It's actually 3, right? I kind of trying to trick you here. The highest power wasn't up front, but it was actually over here, right? So we had x cubed up top, and we have x squared on the bottom. So we're definitely going to infinity or negative infinity. Since this guy's negative and this guy's positive, we are going to negative infinity. Any questions on this one? Right, I try to give you a little trick there. So nice job if you got that one right. Looks like John's up top now. Let's go to the next one.
What?
Trying to trick you up a little bit here. These guys are prime things, okay?
I like what the high exponent is right in front.
Me too. All right, looks like we did pretty good. Highest power on the top is 4, right? Highest power on the bottom is 4. So we're gonna take the coefficient of the top, coefficient of the bottom. We should get 1/3. All right. Any questions on this one? All right, I feel like everyone's trying to answer it the fastest because they really want these animals. All right. Looks like Tommy's up top. All right. Let's go to the next one. Oh God, you can barely see it. It's 3x minus 1 over the square root of x squared minus 6. All right, looks good. Degree on top is 1. What's the degree on the bottom?
1.
1, right? The square root of x squared. The squares cancel out, we're left with 1. So it looks like the degrees match. Coefficient on top is 3. Coefficient on bottom is the square root of 1, which is 1. So we're left with 3. Any questions on this one? All right. Oh, looks like Maddie's on top here. All right. Let's go to our last question. Let's find this limit we've got. All right, we got negative infinity. Why was it negative infinity? Yeah, we got x squared on top and then 1 on the bottom. So it's either positive or negative, but the -2 kind of made it negative instead of positive. Okay. Any questions on this limit? Sounds good. All right, let's see who won. All right, we got Sam H on 3rd place. We've got Tommy 2nd place. 1st place is Maddie. All right, congrats, Maddie. You won, and I actually don't have any other notes for you guys today, so I'm actually gonna let you out a little bit early. Maddie, you can claim your switch.